Okay, hi everyone. I think I'll end up a long time before lunch, so we have time. Anyone who wants to come and informally talk, that's fine as well. I'm going to be talking today about scientific high-performance computing, what used to be called high-performance computing many years ago, when that was the only kind of high-performance computing you had. And I'm going to show two examples how it relates to big data analytics and to large-scale databases. The first one might be a little futuristic for many of you. The second one, I'm sure, will be relevant to most of you. So there's going to be two different application areas. The first one is when you got to do a lot of heavy number crunching. The second one is when you want to do analytics on data you're not supposed to see, because it's private, because it's protected by GDPR, because legally or from the regulator directions you're not supposed to see it, or you don't want the liability of touching it, yet you still want to know things about it. A classic example would be where people are at any given time, or traffic, which is immensely useful to predict things like where a mall might succeed, or should you give a loan to a new business in a new area, but you're really not supposed to know it, and no one actually wants that data on their servers. So two examples. So first, that's the highlight. So as NEC, we're a large Japanese-based company with a few 100,000 people, many of them in Japan, but also in Asia, Europe, etc. We provide traditional and modern HPC systems, the computers. Okay, we have seen, and I will be discussing that there are recent trends in big data analytics, like neural networks, especially deep learning, and also some new kind of time series analysis, does dictate the need for heavier CPU loads. And I'm going to show you some use cases and potentially where it actually applies already today. So when you look at it, high-performance, traditional, scientific high-performance computing and big data are quite different. In terms of functionality, when people said, in the past supercomputer, or now they say HPC, they meant things like weather simulations, thermonuclear simulations, very heavy stuff written in Fortran sometimes, or C, by PhD candidates and postdocs, whereas in big data, it's mostly about database operations. The customers are different. Supercomputers or very large arrays used to be bought by governments or universities. Sometimes several universities would pool up together to buy a 1,000-node or 2,000-node system, whereas big data is done by any enterprise. There is a change in this, by the way, as some of the new customers are actually companies like automotive or high-frequency trading. High-frequency trading use it, of course, for their predictions and for their really fast models. Automotive, can anyone guess what they're using it for? Sorry? Yes, ADAS, exactly. They are running massively parallel simulations of what the car might see as it goes along, and then trying to do training the deep learning. There have been cases where they paid, NVIDIA a check of $2 million just for the GPUs, automotive. So that's a new segment. In terms of the performance metrics, when you talk, to supercomputing guys, it's all about flops, floating point operations per second. How many can you do? How efficiently can you use the processor? Whereas for big data, we're usually talking about transactions per second, right? Because it's all about the business process. The hardware is different. We used to have mainframes in banks. We mostly don't. Some still do. But we have CPU arrays. And in HPC, we are now having companies like Cray, which used to make this famous horseshoe-shaped computer with liquid cooling. They're still making computers, but they're using Intel Lakecrest processors and NVIDIA GPUs. So there's still a lot of engineering in how you connect them and how you tweak the operating system, but it's no longer a core new processor usually. So pretty much, as you can see, everything is different. CIA is different. Confidentiality, integrity, availability is not so important when you're running some simulation. It's important to everyone, but it's not critical. But if it's banking transactions or online advertising, it's got to run. And OK, so we see everything seems to be different. So is there any connection, any thread where the two might meet? So just very, very quick shameless plug. We've been doing this as NEC for a while for the scientific community, not for big data. The recent interesting trend, you can see it here. it's the use of, we have now our vector processor, our latest vector processor. You can still buy it as, big tower-based systems and rack-mounted systems, but you can also buy it like you can buy the Tesla new card K100 from NVIDIA as a PCI Express 2-slot extension. So you can put it in a normal computer. That's what it looks like. What does differentiate this processor from a GPU is that it is a supercomputer processor, which means it's got more memory, but more importantly, it's not an array of thousands of small processors that you compile with CUDA or OpenCL, if you know that. So, in order to utilize effectively a GPU, you've got to program it in the own development environment that NVIDIA or others are providing. Here, these are just really strong processors on this card. So they're like Fortran, C, C++ works. Java is not really used in supercomputing. You could run it, but you wouldn't get the benefits that you're looking for. However, typically, it's perfectly normal to write your application, for example, in Apache Spark or Scala, okay, and use processors like that or dedicated code for running the really heavy stuff, like which we'll show in a minute, like the neural networks or the recommendation system or something. That happens a lot. Actually, Intel now is offering a similar set of libraries that you can hook up with MLlib, the Spark Scala functionality, to get your number crunching done for you using their processors. So that just summarizes what I was trying to show, that a vector engine, as we said, like a supercomputer on a card, doesn't require any special language. You can program using existing compilers with certain add-ons that you just link into them. And it still can process data at the same throughputs as a GPU, so like the NVIDIA. So you don't need to do the special programming, but you can get throughput which is the same or even exceeds that of a GPU. OK, now a general note, which might be useful to those of you who will have to consider or are considering applications like that. This is a general technical note. It's not related to a specific product. Okay? If you talk to any data scientist doing deep learning nowadays for images or for speech or even for finance, they use GPUs a lot. And the way they use it is they just plug it in and they use frameworks like TensorFlow or Keras or PyTorch. And they sort of get the benefits of the speed without having to do anything special for the training, for example. But that only works well for specific problems. In terms of volume, the people buying GPUs and doing deep learning and reporting about it in the open industry, not in the financial industry or the insurance, they use images usually. And the kind of processing, the breakthroughs in the past few years in understanding what's in an image that we all hear about and that we see it in the news, etc., it's all based on two-dimensional convolutional networks, CNNs, meaning, simply put, that we calculate things on a pixel and the nearest neighbors of that pixel. It's all based on a very long sequence of operations like that, where you have 3x3 networks, or 7x7 is the maximum, small ones. For those kinds of operations, a GPU is the natural fit. Why? Because you want to do it in parallel. So you say, OK, instead of just, if I have a big image, I will calculate the convolutions on this part with this subprocessor, this part with this subprocessor. It's perfect. Each one of them gets a small chunk of the image of the resulting layer, does something very well defined on it, and sends it up. And the more instances you have, the stronger the GPU, the better off you are. And that's really what NVIDIA has been doing in the last 3 years, giving you more and more small CPUs like that on the GPU. They're not much faster, as people said, because of Moore's law. You cannot push the megahertz or the gigahertz too much up, okay? But you can put more. And that's great if that's what you're doing. But if you're doing other things, for example, on the left you can see, if you're doing speech recognition, if you're doing medical image analysis, which is three-dimensional, like in MRI or CT, this methodology no longer works. The small processors that the GPU offers you are too small. They don't have enough computation power and enough speed and enough memory. Okay? To give you a very concrete example, if you talk about 3x3 or 5x5 convolution, 5x5 means you've got to put in 25 numbers. And if you're using several channels, it will be maybe 3x3 by 256, so about 2 kilobytes of data. 2 kilobytes of data, that's fine. You can allocate that to each of the micro
GPU processors, and no problem. But if you're doing medical, your chunks in CT or MRI would typically be 64 by 64 by 64. It's 3D, right? Or 96 by 96 by 96. And you're talking hundreds of kilobytes. Not only is the small GPU processors, they can't handle that, and they got to go out to external memory. Even Lake Crest processors, the cache of the CPU is not big enough, the internal cache, not the L2, the L1 cache. So that's a problem. For these kinds of things, strong, heavy vector processors like the one we're making, or the heaviest Intel processors with a lot of L1 and L2 cache, they're your only way to go. And that's a scientific thing. It's like you can do the math. So it really depends on your application. Now, I'll just show a few examples of where supercomputing or really strong processors that do floating point actually apply. I'm not sure. I'm hoping one of these may relate to some of your industries. And after I'm done with that, we'll go to the part about privacy preservation. So one example that many people are talking about is recommendation engine, or what's known sometimes in some industries as next best offer. Meaning, there was a guy in a different session talking about the Spotify example. That's a classic, or the Netflix. You have users that have chosen a lot of things in the past, like movies or songs, and you have many other users. And you're trying to collaboratively figure out if that user is interested in this kind of music or this kind of movies, I'll show them that. But it's not only in these areas. The same is true if you're trying to offer them other products. The point is we have millions of users, and we know what they have done in the past, and there's got to be a way we can leverage that. Okay? So basically, even though it sounds like very far from that, it's actually solved by matrix factorization, or ALS. ALS, the name first came to being as a practical solution. If you recall, a few years ago, Netflix had the $1 million challenge, saying, we have a system for movie recommendation. If you can show us, based on our own data, that you can make better predictions, we'll pay the winning algorithm $1 million. Okay? That was 7 or 8 years ago, and the algorithm was ALS, which is just a faster way of doing matrix factorization. To make it very concrete and to give you an example, what matrix factorization does is you have this big matrix of the users and what they chose. And by the way, it can also be the users and what they've seen on the internet and what they clicked. So the events per user don't have to be something you consumed. It can be something which characterizes you, like which kind of news sites and sub-news sites you go to. It can be any stream of long data that you can put as a big vector. So you have a long vector, a long row, but you have many rows. So you have this matrix. It's not square. Okay? The matrix is not square. The number of users and the number of features have no intrinsic relation to each other. Okay? And you're really looking for smaller matrices, the two here, that their product will make something very similar to this matrix in some sense. Now, I won't go into the math, but to give you a very nice intuition of why it works, let's talk about, for example, music recommendation. When you take a given user, now you have a row, just one guy or one lady that did some things or consumed some content. That's a row. You multiply the rightmost matrix with it, you get a small you get a small vector of numbers. Maybe you had 200 features or 300 features. A feature could be time of day. A feature could be the last thing you clicked on in an ad, anything. But suddenly, out of all of this, you get maybe 10 or 20 numbers. And based on these 20 numbers, the matrix on the left, the one that's standing up like a tall building, gives you the most recommended or most natural offers. Now, let's do a simple example. If you're someone who likes rom-coms and action movies, okay, you can show that what this matrix, the small set of numbers, will actually indicate that. So basically, the system is figuring out what you like. That's the small set of numbers. And then based on that, offering you something from an ever-increasing richness of sets. As most of these things, if you had 20 good data scientists, hardworking, very diligent, and all the time with you, working all the time on these data sets, they sometimes would do better than these algorithms, or as good as them, because they would continuously try to figure out and find new trends. And okay, these rom-coms are different from those, and people that like Bruce Lee movies don't necessarily like, other kinds of action movies. They could do all of that, but you would need many of them working all the time because it continuously changes, and that's the real headache. There is no magic here. The systems work well, but their biggest importance and value is that they don't necessitate so much manpower poring over the data all the time. Okay? So this example, for example, requires a lot of training samples. You can do similar things for fraud detection. User might be someone who's doing certain operations like financial transactions or buying things on eBay. It doesn't have necessarily to be a content product. However, for us, the HPC load is not heavy enough. I mean, when you look at these systems, there's always two parts of computation. It was mentioned yesterday in the Iguazio session, the guy from Iguazio. Actually, most of your work and most of your computer time, like end-to-end time, is spent on preparing those matrices, for example, in this example. Because you don't have these matrices as they are, right? You have a giant Netflix database. Usually, it would be either a clickstream database, a log, Apache log files, and you would have to read them into something and transform them and do ETL and do data validation. You have to do a lot of stuff involving a lot of files from a lot of systems that are spread across all your front-end servers to create the matrix. So even though in that part there's actually no heavy calculation, it's all if, then, else, compare, or put some number somewhere. It's very simple calculations, but it's very slow. So in this case, if the HPC, if the part of actually diagonalizing and breaking down the matrix into these two matrices, the algorithm takes only a small fraction compared to actually preparing the data. So simply put, this is an application where you're probably better off just using regular CPUs. Okay, that's the conclusion of this long story. Okay, but another example, which some of you might be interested in, fraud detection or cyber. Okay, which is actually, by the way, everyone knows what's #1 application of Splunk, for example? Cyber. Splunk was done for, was made for big data in general, but they found out that the largest volume, and they're charging per volume, customers are the ones using it for cyber. Why? Cyber uses information created by computers, and computers create much more information than people. If you have a data center of 1,000 or 2,000 computers, they generate so much log data. And the whole idea of cyber is trying to pore over it, trying to find some correlations between something that happened today and something that happened maybe a week ago. So it's giant volumes of information. Fraud, the same. Fraud is not necessarily all happens in 1 second. Actually, the smarter fraudsters use things that take a long, distributed, seemingly unrelated list of transactions that are spread. They know that if they'll try to do everything in 1 minute, you'll say, OK, what's going on? So they're very clever about it, and they will split the purchase into a lot of small purchases. They're pretty good at what they do. That's why they're successful. So these two applications, what they have in common is you're trying to find something anomalous, right? You don't know what you'll find, but you're saying, I have a system. People usually, they go to eBay, they buy these kinds of things. That's the kind of frequency. Or in computers, I have a data center with 2,000 servers, and they typically do this or that, and they do repetitive tasks, right? And suddenly, something has changed. Now, anomaly can also be that you're having a large system maintenance. Okay, so not every anomaly is necessarily a bad thing. But when you're trying to do an anomaly, and that might be relevant to a few of you, traditionally, people use things like clustering, k-means clustering, and others. Actually, here, neural networks are doing some fancy and effective work. They're being used by eBay, by PayPal, and many others that don't discuss it but are using. The reason it works is what you're doing, really. That's just for fun. I want you guys to know about something about it, so if you're interested later, you can follow up. You're telling the network, I want you to squeeze. Remember, we talked about how users do a lot of things, but at the end you say, actually, I want to characterize it with a small set of numbers, like you like these kinds of movies or these kinds of movies. You're forcing the network during training. You're giving it huge chunks of the normal behavior and tell them, that's normal. See how well you can compress normal to a small set of numbers. Okay? Once you manage to do that, anything which is not normal will almost always not compress well. So when the system will try to reduce the data set, okay? So if you're a guy that doesn't like a specific kind of movie, let's say you're a fraudster of Netflix, and you're just randomly picking up movies, and you're watching many movies, you will not fit the patterns. So when the computer will try to compress your behavior into a small set of numbers, they will be different from what usually you get. They will not make sense. And that's mathematically easy to spot. So that's how actually fraud analysis works for many people. And it used to be just clustering that you can find on any library, but it's becoming now a very strong application of neural networks. And by the way, these are deep neural networks. You can see here a sample layer from an antivirus that's using, we have 6 or 7 layers here. And the reason is just you can't do it any other way. You cannot tell the system, take 1,000 numbers and make them into 10 and get good results. You tell them, take 1,000, make them into 100. OK, that's pretty good. Then take the 100, make them into 50, 20. That's the way it works. So that's why it's a heavy computation. So actually here, if you have a system like that, doing the actual floating point or fixed point calculations is going to be a large part of your computation. And that's a place where you might want to consider higher-end processors rather than a large, very large array of lake crests or others. Another interesting example, which does relate to some industries, is document classification. Now, when people say that, people start to think about things like, I don't know, libraries, or that's not what we're here about. A document can be a post in a forum of an unhappy user in a customer service forum. It can be someone writing a review about the hotel room they were in. It can be a post on Facebook. It can be a rant, a general political rant or something. Doesn't matter. The point is, when we read, I mean, if you, for example, talk to customer relationship managers in a big organization where you have some forums or way of interacting with users, they would look at posts or written text there and say, OK, this guy is complaining about that. That's a general, well done, keep it up message. They already have in their mind some way of classifying, because that's how they decide, you handle that, that is high priority, that is low priority. Sometimes they even have written rules for management, like if someone says they were discriminated against, that's very high priority, you must take care of it. But you need people, and actually that's a large part of the reason you pay those people a lot of money, to do this classification and to notice new trends. Document analysis, it's a different algorithm. I'm not going to go into that now. I'm not going to bore you with that. Anyone who wants more details, come to me. But it's a well-known method, first used on large data sets like Wikipedia, where you say, here's a chunk of documents, any kind of text. It could be also text obtained from speech processing, okay, of a call center. Here's a chunk of text. I think there should be no more than 30 different categories here. The number is something you dictate. But you say, my intuition is that's as much as I can handle. 30, 10, 5, 100, doesn't matter. Find a way, you're telling the computer, to find the right terms, the right keywords in the text that will help you classify into 30 or 10 or 100 different contexts, and then classify new documents as they come about. This was first done on Wikipedia, which is a very nice set of documents, and you also kind of know the classification, because when people enter a new value into Wikipedia, they're supposed to give you some tags about what they think it's about, and it works beautifully well. You can recognize whether a certain Wikipedia page is about history, about wars, about politics, about religion, and of course, if it's about 2 or 3 of them at the same time, you get relative scores to that as well. So that kind of calculation is also quite heavy, requires some kind of supercomputer, or at least very fast, or a very, very large array of regular computers. And people actually use it in industries like restaurants, insurance, by the way, to get customer response. By the way, they also use it about what people write internally. There are fields like, in fields like the medical field, doctors, part of their training is how to write up their summaries. It's not just the language, it's what the department expects them to write and not to write. There's a certain way it's done. Same thing when people write about analysis of insurance claims. When you have a car accident, the report the company writes has to be under certain terms. Using this method, you can find out very easily what was this about. Did the person categorize it the right way, or is it strange? Is it very different from normal? You can do all of that. IBM was the first to do that, but there's others doing it now. And last but not least, in the financial sector, you have all those Monte Carlo simulations of assets, right, of the value of assets. The point is, nowadays, it's also regulated in most countries. The point is, you come to the bank, you say, like, OK, you gave $1 billion worth of loans. How much you got? They say, we've got 200 million, which we are supposed to have to cover up 1 billion. We're fine. But could these 200 million, which are assets, they're not cash, could they become 150 million if something small happens? If we have some trade war, or if we have some bad news, or I don't know, if some team loses in the Mondial, You want to know that. So nowadays, you're regulated to build simulations and to run simulations as any financial institution of what you have and how it might be affected. And that's heavy computation as well. That's very heavy. Actually, here, the data is not so big. You would say, come on, stocks, it's so much data. It's not that big. You can download everything that happened in the stock exchange in terms of not individual trends, but stock values, daily stock values. You can download it on a mobile and process it. But there's a lot of simulations you're running. Okay? So that's another area where heavy computation and not just heavy database operations come into play. Okay, I won't go over this, but basically we are working very hard at optimizing that to making it run faster on our processor. And now let's go to that. I don't think the audio works here, but let's talk. This is from the movie Sneakers, if any of you has seen that. I strongly recommend it. It's so, this movie foretold many of the problems we're seeing today in cybersecurity. It was made in 1992, 26 years ago, and it talked about what happens when someone manages to make to develop not a code breaker, but the code breaker, something that breaks all encryption. And those of you who have been following some discussions and press releases about quantum computing and other things, and even if you're just following the regular press, basically any encryption method that people have commercially used in some setting in the last 20 years, GSM, 2G, 3G, RSA 512 bits, WPA, all of them were broken within less than 10 years of being commercially used, which means that, okay, you might not be, if you have a transaction happening now and you're using present-day encryption considered good enough, you're fine. But if someone got that file, you're not assured at all that within 10 years they won't be able to decrypt it. With future technologies you don't have right now. The problem with cryptographers is that they're so good at inventing new methods, cryptography methods, but they're also so good at breaking them. So basically, if you look, for example, in the year 2010, there were still some third parties of large organizations that were using 512-bit RSA encryption because 10 or 15 years ago it was considered good enough. But in 2010, already if you were willing to spend a few $1,000s, in 2010 you still needed the computers yourself. Nowadays you just buy Amazon instances, rent them. There are services where you can tell them, this is a WPA session, or this is a WAP session where I have some guess about some things, or this is a hash value of a password, and I want you to try to break it. And you just pay them money, not that much, by the way, and they just break it for you. You don't need to be a cryptographer to do that. So am I saying you can't use encryption and we're all doomed? No. But I'm saying if you have important information, like someone's financial transaction, financial bank number, and address, and you're saying I'm just relying on encryption when I share it with my partners, that might not be good enough in the long term. Because right, the way we do it right now, the way we protect data right now when we share it, and the API economy is all about sharing, whether we like it or not, is we tell our partners, I expect you to hold up to certain crypto standards, right? If two banks are corresponding on some transaction API, they say, okay, it's a bank. They're serious people, they might even have some reviews, to talk about cyber between themselves. But when the network becomes so complex, when this bank is connected to other organizations and other organizations, eventually one of them will have, unintentionally maybe, a lower level of security. And your files will leak, or they may leak, or some of your log files, because log files of APIs between two banks actually hold everything you want in them, or at least a large part of it. So they will not be broken now if you kept your encryption well, but they might be broken in 5 years, and in 5 years, that's still very valuable in many cases, right? People don't change their bank accounts so often, and unfortunately, usually the amount of money we have there doesn't change so much within 5 years. Sometimes it does, but for good or bad. But usually, if I have your financial records from 5 or 6 years ago, as a company or as a person, I know some pretty good stuff about you. Okay? So everyone's talking about how can we protect better, or how can we still share information, because it's all about sharing. We do want to share certain types of information while still being protected. And the problem is implementation. It's hard to implement. Future protection, which I just mentioned. I do something now. Is there a chance that within 3 years, some smart cryptographer of some country will find a way to break it? Then I have to redo it all over again. That's a nuisance. and validation. When you do high-level security design nowadays, you can't just say, I use that and I spent $1 million on it and it's fine. You are validated by independent consultants, either by your insurer or by your CISO or by the regulator. So it has to pass validation, your design. And that's becoming more and more of an issue because people who have never trained to do that find it very hard to do. So, and these are just examples we all know about of recent breaches. So it turns out that 30 years ago, over 30 years ago, mathematicians who are always, very forward-thinking, found out actually a way to protect against those things called shared multi-party computation. It's very slow, okay? So that's why you haven't heard about it so far. For reference, RSA, public key cryptography, was basically invented in the 70s. But in the 70s, you couldn't really do it practically unless you were willing to spend really a lot of money. Took some time, the internet came, the application came, and it was used. Same thing here. If you wanted to do this kind of computations 20, 30 years ago, maybe some governments did. I don't know. I wouldn't be surprised. But it was way too complex and expensive. It's not just CPU. You need a lot of communication. Nowadays, you can run these algorithms properly optimized. Okay? If you know what you're doing, you can run them on an AWS region. We have done it. And get things like, for example, a neural network running on data safely without seeing the data and giving you a result in 100 milliseconds. So what can you do with it, really? You can do with it joint marketing, meaning get more information from other entities. You can do anti-fraud. You can do anything that people right now use big data for, running on data, that right now the only way to do it is they say, OK, give me the data. I will treat it with the utmost respect, delete it after I'm done, and give you the result. And they're not happy about it. I'll give you maybe just very quickly an example. Without talking too much about ourselves, I'll give you a very quick example. MasterCard. OK, that's a pretty real-life enterprise. MasterCard shared with MIT a few years ago. We're working with MIT on that as well. Shared with them data of how consumers in a certain country where it was legal to acquire this information, what they bought, actual products they bought and where they bought them, where they were during that time, and their government information like marital status, address, education, kids, all the employed, not employed, all of that data. And lo and behold, MIT showed MasterCard that within 1 month of work, not even very hard, just running the regular packages, when you had all this information together, you could predict much better if this person is likely to run into debt, not pay their loans, or not pay their credit card monthly use, or just increase their usage very much. Really, very basic analytics. So we know that when you know more about people, you can serve them better. Okay? You can market to them better, but you can also serve them. Problem is, you're not allowed to have this information, and you don't want it either. Okay? So what can you do? So for example, using SMPC, this method, we implemented it. Rather, it's quite easy. You write it like you would write any Python script, pretty much. Only you have to take care of some rules that you have to know. But the code itself is very simple. Basically, any computation that your data scientists are using right now for inference, for classification, for recommendation, you can rewrite using SMPC. So the idea, going back to the root of it, is several entities have data. They don't want to share it in any way. It's not like sharing, but, oh, it's very encrypted. They don't share the data, okay? And still they're able to get the results they want, the analytics. So in this example, you have two companies. One's the insurance. The other is the bank. Imagine, I can tell you, we talk to large insurers. They would love to get the bank's opinion about a certain customer when they give them their offer. It would help them a lot. But of course, they can't talk, okay? But just to show you a very simple example, because it sounds like magic or like snake oil, that's how you add two numbers using this method. Okay? So if we just have, like, let's say, two billionaires want to combine their average or their sum of their money, but someone else wants to know it, or you want to calculate the average salary in a company or in a small town, but people don't want to hand out the information to you. They don't want anyone to know how much they're making. You can do it using that. The way you do it is you take each number or each feature vector and you split it. And I won't go into any more math. But basically, you split it into 3 segments that the sum of them is the original number. And this splitting is done randomly. And you send chunks of these 3 numbers to 3 different servers, or 4, or 5, but it can't be 2. Okay? And each of these servers is handled by a different entity. So for example, to give another simple example, I want to do biometric authentication on someone. The biometric signature, how do I do that? I take your picture or your speech or your thumbprint, and I calculate I create a feature vector, and I compare it to your biometric signature. But this biometric signature has to be stored somewhere. And if someone ever hacks that server and gets this data, you're done, because you can change a password, but you cannot easily change your face or your fingerprints, right? So that's one of the reasons why companies don't want to do it. They say, I don't want this data. I definitely want to be able to do 2-factor authentication. I want to make sure my users are who they are. They're doing banking while they're flying from Singapore to London. I want to make sure it's that guy. It's not some fraud. I want to do that. I want to check their PC. I want to see it's the same PC they used last time. I want to do all those things. But I don't want the liability of having this data with me, because if it ever gets hacked, I'm in for another Experian or Equifax disaster. Imagine, instead of having this information, you split it in a cryptographic way between several servers, and one of these servers is managed by Ernst & Young or PwC, some trusted third party or some legal firm, and the third one is managed by a government, the regulator itself. Then you are protected. No one can just steal the data on your servers as a company and create this situation. You are protected, okay? To give you a very practical example where these things are now being implemented, let's say you want to check that your accounts are compliant, do compliance checking, or money transfer between organizations, settlements of payments. That's a very sensitive area because there's a lot of fraud there. Like, you look at a big multinational corporation, suddenly you find out $600,000 were paid for cleaning services to a company that no one knows about. I think the most juicy example was, maybe you read, there was a company a few months ago. There is a very respected computer company called Qantas, I think, Qantas, and there was a fake company somewhere in the former Soviet Union, fake set up, supposedly selling computer equipment, and they managed to sell equipment which was never delivered to the large accounting departments and get paid for it of very respectable companies for a total sum of $120 million. That's not small potatoes. Do you know which companies those were? Anyone? You use them every day, Google and Facebook. These guys are so smart at figuring out things and doing TensorFlow and all that, but they just paid each several tens of millions of dollars for computers they never received. So anyone might be fooled, okay? And that's the story you hear about. There's so many others you don't. So again, how does this relate to this? Basically, it's not so hard to say this is a repository of data of what I allow and don't allow for transactions. And these are the rules, the if, then, else. And these are the account numbers. And anything which doesn't work according to those rules, I want the CEO or the CFO to have a look at. That's easy enough. Problem is, how do you trust the guards? I mean, the guys who are supposed to execute that, or the server who's supposed to execute this check. So what you do, you split it using MPC, and then each of the computers doesn't actually have the transactions. See, the point is, there's companies out there that can make these rules for you and verify the accounts for you and check for compliance. They can do that for you. That's their specialty. But it's a very hard decision to say, I want them to do that for me, because then they have all my information. And then, it's a big firm, maybe 20,000 employees. How do I know where it's getting? Using MPC, you can do that. You can actually, as long as the algorithm is defined, you can actually run the algorithm using several computers, and not one of them has any access. It's not like we're splitting important records and one gets a third and the other gets a third. If you have one of those computers, all the data and all the transactions it ever handled and all the communication, you cannot deduce any. So the kinds of things you can do, just to recap, you can do private key signatures where the private key itself is split between 2 or 3 computers. You can do biometric authentication. You can verify your partners in an API transaction, okay, if they change their computer or operating system or anything. You can run analytics. You can do, I mean, that may sound like a not sexy application, but doing monitoring of the other party in an API transaction is quite useful because there's continuously more and more APIs, and the big problem about APIs is that it's just computers. You know, if someone sends, you know, if you have financing departments all done by hand, and suddenly they get, you know, $1 million transferred to the Cayman Islands, the person's going to say, that's interesting. Maybe I'll ask someone. It's not efficient, but in these kinds of things, you know, the nosiness helps. But if it's APIs and they've been working perfectly for a year, you want to make sure tomorrow something like that doesn't go through. That's when you need these kinds of things. And basically what I'm trying to say here is NEC is in this eventually, of course, for, you know, creating a business. But right now, it's very early days. We've had only a few proofs of concept. Anyone here or anyone you know of who's interested in trying to implement that, we'll work with you. We're not in this to charge anyone for any money. We're interested to make some of these methods work. We'll probably open source eventually the solution. There's still a very healthy business once it becomes accepted in, you know, actually doing the commercialization. So anyone you know who might be interested in a sample use case, we'll be very happy to talk to you about it. OK, thank you very much.